Welcome back to the lesson on adding and subtracting geometric vectors. So now that we know how to add and subtract vectors, we'll take a look at a couple of examples where we can apply the skills we just learned. Now, before we start, I want to review with you or recall a couple of formulas that are very important and very useful when dealing with vectors. Number one, SOHCAHTOA. Remember, SOHCAHTOA is the acronym for sine, cosine, and tan ratio, and they're used to solve right-angled triangles. Another set of formulas that we use very often are the sine and the cosine law. And sine and cosine law, if you remember, can be used in any kind of triangle. So for this triangle, ABC, where angles A, B, and C are different from each other. Remember uppercase letters for angles, and we use lowercase letters to label the sides. Then we write the sine law as A over sine A, so side length A divided by the sine ratio of the angle A, which is opposite to the side, equals B over sine B equals C over sine C. Cosine law, on the other hand, is very similar to Pythagorean theorem. So C squared equals A squared plus B squared. Pythagorean theorem is applicable only or can be used only in right angle triangles. Cosine law is in any triangle, and that's why we see a third term on the right side, 2AB cosine C. Now let's get started with our first example. We have to find the magnitude and the direction of the sum of two vectors, u and v, where u is 3 units and v is 4 units. The angle made between the two vectors is 65 degrees. So read the problem for a second time with the intention to, really understand the information given. So we have to find two things, the magnitude and the direction of the sum of these two vectors. And we'll always start by drawing a diagram. So starting off with vector u. So I'm going to draw a vector here, and I will say this is vector u. And whenever you draw a diagram in geometry, it's important to label the diagram correctly, and if possible, add the measurements as well, because in this way, when we have all numbers on a diagram, we can see and visualize the connections between the given information and use them appropriately to and accordingly to find the information required. Now, vector v makes an angle of 65 degrees with vector u, which means when vectors u and v are placed tail to tail, the angle between them must be 65. So from the tail of vector u, I'm going to build the vector v, and I'll make sure to draw a 65-degree angle. Again, I'm eyeballing this, and I will try to make sure that vector v seems a little bit longer than u, because it actually is, and I will make the angle, or I will mark the angle in between, which is 65 degrees. So here goes vector v, and again I'm going to write the length of it. Now, first I'm going to draw the vector that represents the sum u plus v. And since the two vectors are already placed tail to tail, I will use the parallelogram law of addition. So here we go. I'm going to start off by drawing a parallel side to vector u and a parallel side to vector v. And I will make this look a little bit prettier so we can see everything, and I will put the numbers in. So this must be 4 units and this one here must be 3 units. So the sum of u and v will be starting at the tail, right, both tails, and then heading towards the angle across from it. So here we go, vector u plus v. Obviously I'm going to label this. And now I have to think of a way of how to find vector u plus v. Again, whenever we start a solving process, especially in geometry, what we want to do is take a second look at the diagram that you've just created and check and see if there are other numbers or measurements you can easily identify without too much work. For example, angles in the shape. So remember, this is a parallelogram. And in a parallelogram, the two angles that are built on the same side of the parallelogram will add to 180 degrees. That's a rule that we've learned in grade 9. So this means that this angle right here must be 180 degrees. Take away 65. So that will make it 115 degrees. So I'll write it down here so that I know that I have this measurement. And next I have to think, what formula can help me find u plus v? Well, that depends on what I'm given. And what I'm given is length u, length v, so these two sides. I know these two, this angle, the angle between u and v, and that makes me think of cosine law. So cosine law will be this side in here squared, which means the magnitude of u plus v. So this is vector u plus v, magnitude of it, put u plus v, the whole expression inside the absolute value squared, equals u squared plus v squared minus 2 times vector u times vector v, always magnitude cosine of 115 degrees. Now remember to set your calculator to degree mode if you are using or if you're given the angle in degrees. And now we have to substitute. Then we have 3 squared plus 4 squared minus 2 times 3 times 4 cosine 115. So I like to use the calculator and leave the answer in the calculator. So 3 squared plus 4 squared, that's a 25. And then minus 2 times 3 times 4, that's a 24 times cosine of 115. And that gives me 35.14 and so on. So I'm going to write 35.1 here, but I'm going to leave the answer in the meantime in the calculator and not delete it. Remember that this represents the magnitude of u plus v squared. I have to find u plus v, so I have to square root 35.1. And in this case, I would leave the answer, as I said, in the calculator and input it inside the square root for a more accurate answer, obviously. And I got 5.9. So I'm not actually specifically required to how many decimal places to round. So I'm going to leave it at 1 decimal place, and I hope that will be okay. Next thing that we need to do is describe the direction of vector u plus v. Now, in order to describe the direction of vector u plus v, we can describe it in relation to vector u or in relation to vector v. So this tells us that we can either find this angle here or this angle here. So I'm going to start off by finding this angle, and I'm going to give it a name because whenever I use a measurement in a solution, it needs a name, right? So I can call it by a special name, and I'm going to call this angle theta. So according to this triangle, we see that we need to find angle theta. We have the side opposite to it. And we also, and already have found u plus v. And now we know that u plus v is 5.9, which means that we can use the pair of this side length with the angle across from it. So sine law, here we come. So I'm going to write in here the magnitude of u plus v over the sine of 115 equals the magnitude of vector v actually divided by the sine of angle theta. So substitute, so we have 5.9 sine 115 equals 4 over sine theta. Cross multiply. And when I cross multiply, I like to cross multiply first the part that has a variable. And also remember that whenever you have trig terms, it's best to keep the numerical part of the term in front of the trig term so that you won't confuse it with the expression inside the ratio. And that would be 4 sine 115. And sine theta would equal 4 sine 115 divided by 5.9. And if you're wondering if you can cut the steps a little bit shorter, The answer is yes. So once you build up the ratio, you can simply state what the sine ratio is and then write down the answer. So theta would be inverse sine of this value for sine 115. I'm only writing this for the purpose of explaining, but it's not a must show step, just in case you're wondering again. And what I'm getting in here is 4 sine of 115. Divide that by 5.9. So I got a certain number, 0.6144. And I will input inverse sine. And instead of writing or rounding that value I got for this number here, 0.6 something, I will simply input the answer. So I will go answer, and the calculator will give me the answer, and I got 37.9. So theta is 37.9 degrees. So we'll say that the magnitude of vector u plus v is 5.9. So vector u plus v is 5.9 units. And it makes an angle theta of 37.9 degrees with vector u. And voila, that's the answer. Let's take a look at the next example. In the next example, we have to express each of the following in terms of vectors a, b, and c. So as you can see here, we have a 3D shape. So it's a rectangular base prism where we have vectors a, b, and c represent respectively the two sides of the base and the height of the prism. So vector BC, I'm going to draw the vectors as I identify the lengths. So vector BC starts at B and ends at C. So it is going this way. So as you can see, vector A seems to be the same length because there are two parallel sides of the base of a prism, rectangular base prism, but it goes in the opposite direction. So I would say that BC is the opposite of vector A, so negative A. Vector GF. So vector GF starts at G and ends at F. So as you can see, GF would be the same as OA. So that would be equal to exactly A. Vector OB. So OB is a vector that connects O with B. Now remember that this is a parallelogram. So you can tell that vector OB is the sum of vectors A and B. So let me show this here. And we'll write in here A plus B based on the parallelogram rule. So now vector AC. So here is A and here is C. So when you look at this vector here, the vector AC, you can tell that vector AC would be equal to, if we use this triangle, let's draw it first. All right. Okay. So, so this is vector AC, and we can look at vector AC as the sum of two vectors, vector AB and BC. Now remember that vector AB is B and vector BC is negative A. So we're going to say that vector AC is the sum of vector B with negative A. So in other words, this will be the vector B minus A. Now let's take a look at vector BG. So BG starts at B, ends at G. So let's draw this, and we'll make it pink. So here goes vector BG. So when you look at vector BG, we can interpret it as the sum of vectors BF and FG. Now vector BF is the same as OD, so that's C. And vector FG is the opposite of A, so that must be C plus negative A. So that makes vector BG equal to C minus A. Vector OF, it's getting crowded here. So let me make this a little larger. So vector OF starts at O and ends at F. So if you look closely at this diagram, you can squint your eyes if you wish, you can probably see, and I hope you can see, that here we have a right angle triangle because this is a right prism. And this angle here would be 90 degrees. So let me just quickly draw this. I'm going to have to use a more unique color to describe it. Okay, so orange is beautiful. So OF. Here is vector OF. So OF would be equal to vector OB plus vector BF. Now, remember that vector OB, we already found, that is equal to A plus B. So we'll say that we have OB plus BF. I'm going to show the steps in here to be sure. So OB was A plus B. And vector BF is equal to the height of this prism, so that equals vector C, and they're pointing in the same direction. So the vector that connects two opposite vertices in a prism, rectangular base prism, is equal to the sum of all three vectors, so that represent the width, length, and the height. Now vectors DO and AE. So let's take a look at DO. So here we have D, here we have O. As you can see, DO itself is negative C. Vector AE, so here is vector AE. So vector AE equals exactly C. So if we have the sum of an F vector with its opposite, then this will be vector 0. Next, or last, I should say, we have CE minus CB. So let's take a look at CE. So here is C, and here is E. Remember that CE will be across from, CE is the one that connects the two vertices across from each other. Okay, so what I'm going to do right now is I will have to erase this because it's getting a little bit crowded, and I really want to give a better view at the new vector that new vectors that we're working with. So vector CE. Now here is vector CE, and I'm going to ask you to try to imagine how these two vertices are related to each other. So remember that these are two furthest corners or furthest vertices of the prism, and we're going to build a triangle, and this triangle will be this vector here, CA and AE. Okay, so we're going to say that vector CE itself equals vector CA plus vector AE. Now, on the other hand, we have vector CB here. So vector CB starts here, ends in here, would be vector A. So I'm just going to leave it as CB already. Now, vector CA, as you can see in here, vector CA is the sum of negative B with positive A. If you use a triangle rule, so this is CA again, so that would be the sum of this vector here, vector negative B, and vector OA or vector A. AE is equal to vector C. And vector CB is exactly A. Sorry. Same as A. So we're going to add an A. So therefore, we're going to say that the difference CE minus CB would equal 2A minus B plus C. Now let's move on to the next example, example number 3. Example number 3 says an airplane heads south at a speed of 300 kilometers an hour. So here goes the airplane heading south. 300 kilometers an hour. So this would represent the velocity. It meets a wind from the west at 100 kilometers an hour. So the wind is coming from the west. And what I'm going to do is I will draw the compass right on top. North, south, west is here, and east. So if the wind is coming from the west, it means that it is pushing this airplane further to the left. So here is the velocity of the wind. And it seems to be 100 kilometers an hour, so kind of 1/3 of the speed of the plane. Now, what is the resultant velocity of the airplane relative to the ground? So obviously, if a plane is heading, for example, south, but then we have the wind that is affecting the direction. So we're going to say that the plane won't maintain the same direction, so it won't go south. It's going to go a little further. And that is due to the fact that the force of the wind will affect the velocity of the plane. So the velocity of the plane then will be equal to the resultant velocity of the plane itself combined with the velocity of the wind. According to the triangle rule or law here, this would be the sum. And this would, or the resultant of the velocity of the plane. So we are trying to find the resultant velocity. And then we're going to say that according to the measurements given here, 300 kilometers an hour, this would be 100 kilometers an hour. We have a right angle triangle here, which makes the resultant velocity brought to the power of 2 equal to 300 squared plus 100 squared. So that's 9, 1, 2, 3, 4 zeros, and 1, 1, 2, 3, 4 zeros, and that will make it 10,000. And 100,000 to be more precise. And the resultant velocity, the magnitude of it, would be the square root of 100,000, because we have 90 plus 10 in here. So the square root of 100,000 equals 316. So the resultant velocity will be 316 kilometers an hour. So it is going to go faster because the wind is pushing and is helping with the speed, but it's changing the direction, and we need to find the direction as well. So we're going to call this the angle theta, and we'll say that tan theta equals opposite over adjacent, which is 100 over 300, which makes theta equal to inverse tan 100 over 300. And theta equals, simply use the calculator, so inverse tan 100 divided by 300, which is basically 1 over 3, equals 18.4 degrees. So we'll say that the resultant velocity R equals 316 kilometers an hour. And we can either use bearings, or we can describe the velocity's direction based on the compass. So this would be south, and this would be north, and then east, and then west. So it seems that it is heading from south towards east at an angle of 18.4 degrees. And we'll put this inside square brackets, and voila, this is the answer. Now we have one last example, oh, not one, more than one, to look at, and I am going to make another video for it, so I will see you soon. Bye for now.